Good morning, one and all. First of all, I would like to thank for the given opportunity in front of you. I am Dhanabalan. I am going to present my topic: hyperfine structure, alkali type spectra, equivalent electron, and Hund's rule. Now, first going to discuss that hyperfine structure. Atomic nuclei radii of the order of 10 power minus 4 Armstrong. The nuclei behave than electrons. Nuclei to be positive point charge of infinity mass. Michelson, Fabry and Perrot are explained about hyperfine effects. They produce shift of the electron energy levels less than fine structure. Hyperfine components are observed using high resolution interferometer. Paulis attributed the hyperfine structure to an angular momentum of the nucleus of the atom. Orbitals and spin angular momentum of electron could explain completely the fine structure of spectral lines. Hyperfine structure is caused by the properties of the nucleus. Now we discussed hyperfine structure as simple and clearly. This topic over. Next topic, alkali spectra. That means alkali metals are lithium, sodium, potassium, rubidium and cesium. The atoms of these elements have one electron in their outermost orbit. The hydrogen atom has only one electron as a whole. The spectra of all the elements consisting of atoms having one electron in their outermost orbit are similar and are called alkali spectra. Now, doubly ionized atoms of beryllium, magnesium, calcium and singly ionized atoms of boron and aluminum have only one electron in the outermost orbit. Therefore, the given alkali spectra, in general, the wave number of the same series in alkali spectra is written as nu bar equal to 1 by lambda equal to r into 1 by p minus alpha whole square minus 1 by q minus q beta alpha whole square, where alpha and beta are characteristic constant for the element. Here p are the fixed term and q are the running term. The various series found in the alkali spectra are the following. First one, principal series. Here the principal series for this p equal to 1 and q greater than or equal to 2. Nu bar equal to r into 1 by 1 minus alpha square minus 1 by q minus beta p whole square. Here p represents that principal series. Second one, sharp series. For this series p equal to 2, q greater than or equal to 2. Nu bar equal to r into 1 by 2 minus alpha square minus 1 by q minus beta s whole square. Here s represent in the subscript, s represent sharp series, s called that sharp. Third one, diffusion series. For this series p equal to 2, q greater than or equal to 3. Nu bar equal to r into 1 by 2 minus alpha square minus 1 by q minus beta d square whole square. Here d represents diffusion series. Last one, fundamental or Bergman series. Here p equal to 3 and q greater than or equal to 4. Here nu bar equal to r into 1 by 3 minus alpha whole square minus 1 by q minus beta f whole square. Here also beta represents that fundamental. Here beta p, beta s, beta d and beta f are the characteristic constant of the respective series. This topic over. The next we going to present that equivalent electrons. Among the values of L and S obtained from the general rules for addition of angular momenta are those which correspond to states forbidden by the Pauli principle. Examples: configurations np square for each electron. The following values are possible: ml equal to 1, 0, -1 and ms equal to plus or minus 1 by 2. Combining the different values of ml and ms, we obtain the following possible states. Here ml equal to 1, ms equal to 1 by 2, that state plus 1. Similarly, ml equal to 0, ms equal to 1 by 2, the state 0 plus. Here ml opposite minus 1, ms equal to 1 by 2 is a minus 1 positive term. ml equal to 1, ms equal to minus 1 by 2, 1 negatively 1. ml equal to 0, ms equal to minus 1 by 2 is a forbidden, that means 0 minus, 0 negative. ml equal to minus 1, ms equal to minus 1 by 2, fully negative terminal, minus 1 negative. Next one, in each of these states there cannot be more than one electron. The following states with non-negative values of ml and ms are possible. Here given state ml, ms. So you see here in the state right side, any negatives are presented, the ms also 0. Let's consider third term onwards to last term. In state left side, this will be varying. For example, 1 positive, 0 positive, both are positive, that means 1 1, ml1, ms1. 1 positive, minus 1 positive, 0 1. Similarly, this process repeated up to end of minus term. It also presented. Again I will read this. 1 plus 1 positive, 0 negative, 1 0. 1 positive, minus 1 negative, 0 0. 0 positive, 1 minus 1 0. 0 positive, 0 minus 0 0. Minus 1 positive, 1 negative, 0 0. State with negative values of ml and ms need not be written out. The presence of the ml equal to ms equal to 0. The term shows that first d, that means first term d term is among the possible terms. To this term we must further assign state with ml equal to 1, ms equal to 0 and ml equal to 0, ms equal to 0. Among the states left is that state with ml equal to 1, ms equal to 1. This and states with ml equal to 1, ms equal to 0 and ml equal to 0, ms equal to 1 and ml equal to 0, ms equal to 0 yield the third term, and that means 3p term. The only remaining state has ml equal to 0, ms equal to 0. It corresponds to the first term, first S term. Thus only 3 terms are possible: 1d, 3p and 1s for the configuration np square. The possible terms for the configuration np cube are 4s, 2p and 2d. The possible terms for the configuration np power 4 are 1d, 3p and 1s, the same terms as for the configuration np square. This topic over. Next going to the next topic, Hund's rule. Hund's rules are here three rules available. Described that Hund's first one, in first rule, the term with maximum multiplicity lies between lowest in energy. The lowest energy atomic state is the one that maximizes the sum of the S for all the electrons in the open subcell. Consider the ground state of silicon. The electronic configurations of silicon is 1s square, 2s square, 2p6, 3s square, 3p square. Is a spectroscopic notations we know already. We need to consider only the outermost orbit 3p square electrons, for which it can be shown that the possible terms allowed by the Pauli exclusion principle are 1d, 3p and 1s. Hund's first rule now states that the ground state term is 3p, which has s equal to 1. The superscript 3 is the value of the multiplicity equal to 291 equal to 3. The diagram shows that of this term with ml equal to 1 and ms equal to minus 1. This diagram I will present last one. Rule 2. For a given multiplicity, the term with largest values of L lies lowest in energy. For a given multiplicity, the term with the largest value of the total orbit angular quantum number L has the lowest energy. Electron configuration 1s square, 2s square, 2p6, 3 square, 3p6, 3d square, 4 square, open shell 3d square, and the allowed terms include 3 singlets, that means 1s, 1d and 1g, and 2 triplets 3p and 3f. We deduce from Hund's rule that the ground state is one of the 2 triplets, and from the Hund's second rule that the ground state is 3f. That means here L equal to 3 rather than 3p 9 with L equal to 1. And there is no 3g term since its ml equal to 4. There is no 3g term since its ml equal to 4, ms equal to 1 state would require 2 electrons each with ml equal to ms equal to plus 1 by 2 in violations of the Pauli principle. Last rule. For atoms with less than half filled shells, the level with the lowest value of J lies lowest in energy. This rule considers the energy shifts due to spin-orbit coupling. In this case, where the spin-orbit coupling is weak compared to the residual electrostatic interaction of L and S are still good quantum numbers, and the splitting is given by here given the 3p lowest energy term is Si, that means silicon, consists of 3 levels with only 2 of 6 possible electrons in the shell. It is less than half full, and thus 3p0, that means not, is the ground state. For sulfur S, the lowest energy term is again 3p with spin orbit levels, but now there are 4 of 6 possible electrons in the shell, so the ground state is 3p square. This is a pictorial representations of Hund's rule. Like here, 2 type of diagrams available, and this explanations. Within a subcell place, one electron per orbital before pairing them. Yes, that means this rules based on that empty bus seats. Here first filled each and every cell singly, then remaining any electrons available, then come to starting from first onwards. It is not sitting in the same positions in the same orbit. There are no two electrons cannot be entered. These rules also like Pauli's exclusion principle. This topic over. Thank you for your watching. Thank you.